All right, so today we're going to take a look at section 1.1, which is called Mathematics and Problem Solving. And we're going to start with something called the four-step problem solving process. A mathematician named Polya is credited with this process for solving problems. The first overall step when you're looking at a problem is to try to understand what's going on. What are you being asked? So these are some of the questions that you might be asking yourselves as you sort of decide, do I really know what I'm being asked? Can the problem be stated differently? What is it that I need to find, or what is needed? What are the unknowns? What information is obtained from the problem? And what information, if any, is missing or not needed? And when you think about real life, not real life problems in a math book, there's usually information that's missing or information that's not needed, right? Extra stuff that's not irrelevant to this particular, question that's being asked, kind of things. After you kind of have a good understanding of the problem, you got to figure out how you're going to solve it. You're going to devise a plan. And we're going to look at several of these strategies in this lesson. But these are a few strategies that you might employ. So this says it's a non-exhaustive list of strategies, which means there are others. These are just some of them. Looking for a pattern. Interestingly enough, we were at a location where my 5-year-old was throwing a dice. And this dice was a 6-sided die, and it had emojis on it. And one emoji was winking, and one emoji was going like it was really excited, and one emoji was smiling. And it was really funny because as my daughter threw this emoji thing, and then it was duplicated so there were 6 sides, but they were really just 3 different images on them. So as she threw this dice across, it kept going, like there was a pattern, and it was really funny. And so I was actually working with her on patterns just because it happened, like in real life. She threw the emoji icon, or she threw the emoji die, and the first one was a happy face, and the next one was an excited face, and then it was a happy face, and then it was an excited face, and it was a happy face. It kept going back and forth between the two. It never even landed on the third one, whatever I said it was. And so I would ask her, what do you think it's going to be next? Right? We were looking for a pattern. Examine related problems. You guys have done this before when you say, oh, look, it's just like that one she did in class. Or, oh, look, it's just like the problem I just did. It's a similar problem. Examining a simpler or a special case. So often if you can minimize the sort of the chaos in what's going on, you can figure out the general steps to something by using a simpler example. Making a table or a list. How many of you are list makers? Like you write down the list and you maybe even add to it so that you can mark it off the list? Yeah, me too. So making a list is often really helpful in a math problem, creating a table or a list. Identifying a subgoal. Sometimes if you can just figure out if I could just get to this point, then I know how to finish it from there. That's a subgoal. A diagram. Have you ever drawn pictures in a word problem? You don't even have to be a good artist. Pictures are helpful in some cases. Guess and check. Did you know guess and check's okay? Randomly guessing and checking is not super helpful, but guess and check can be a very good strategy. Working backwards, and I know you've done this one before too. This is what happens when you look at the back of the book and you say, hey, look, the answer's 52. How'd they get that? Right? Have you ever done that? I have, right? And you're trying to figure out by working backwards. It's like the mazes. Did you know it's always easier to work a maze backwards? Yeah, it is, right? It just is. Writing an equation. So writing an equation is one of those ones that we're not going to work a lot with in this class. There's nothing wrong with it. So if you see a problem and you want to write an equation to solve it, I'm not going to tell you can't. But that's really kind of above the pay grade of what the content requires. It's not necessary. There's no need to do an equation for any of the problems that we're going to encounter, at least not the way you're thinking about equations from a high school standpoint, okay? But it's okay if you use them. I don't have a problem with it. After you've decided which plan you want to try, you're going to try to do the plan. So you're going to carry out the plan. Implement the strategy that you figured out. Perform the necessary actions or computations. Be careful to the language, the precise language of mathematics being used. Check each step of your plan along the way, either formally. So formally means like you double check, did I really multiply that right? Intuitively means you look at it and go, does that make sense? right? Did it make sense that I got a 4-digit number and you look back and you're like, no, it really should have been a 3-digit number, right? Intuitively. Keeping an accurate record of all your work. If your work is spread all around and you don't get the right answer, it's really tough to go back and figure out where you made a mistake for you and for the grader or me, all right? So keeping a good log of what's going on so you can figure out what's the next step or maybe where mistakes were made. And then in the very end, after you have your answer, checking your work. So checking your work involves 2 different things. One is about reasonableness. Does it make sense? Right? So when I ask a question about how many babies, and you answer 42.3 babies, does it make sense? Right? No decimal points of babies. And then there's the issue of checking accuracy. Accuracy means the actual computations. Did you really multiply 4 times 12 and get 48, or did you accidentally write down 84? Or whatever, right? Accuracy, that's the other part. So what we're going to do is we're going to try to do one problem today of this problem-solving strategy. And the one that we're going to look at, problem number 1, is about a mathematician named Gauss. So Gauss was a very important mathematician. This is actually something that happened in early grade school for him. His teacher gave the class an assignment, wanting it to take a good deal of time, asked them to find the sum of the numbers from 1 to 100. I'm sure you would never do that. Just try to give your kids busy work kind of thing. I mean, like, it's not exactly busy work. Like, yeah, they need to know how to add. But you know what I mean. You would never do that, right? Oh, okay. So, unfortunately, she had Gauss in her classroom. And you will probably have some child along the way. His name will probably not be Gauss. That's his last name, too, by the way. But yeah, you're going to have this kid where they do something and you're like, how did they do that? What did they do so fast? So Gauss answered almost immediately. So what I want to show you, because it's a very interesting thing that he did, is what he did to solve this problem. And he probably didn't do it with quite as much structure as I'm going to show you, but the structure helps to see what happened a little bit easier. So we're going to sort of put our own structure on the top of his problem-solving strategy. So this is literally what his teacher asked him to do. She asked him to do 1 plus 2 plus 3 all the way up to 100, okay? And I'm going to add the last 3 numbers here. So 98, 99, 100. Everybody good so far that this is the question being asked? Okay, so this is kind of like step 1, understanding the problem. This is the problem. So here's what Gauss did. Gauss said, well, you know what? It's very interesting. If I add these numbers together in reverse order, like this, and I do that whole thing where, you write the line like they do there in elementary school, right? And you add them up sort of like vertically down. What do you notice happens when you add 1 plus 100? What do you get? You get 101. And what happens when you add 2 and 99? You get 101. And what happens when you add 3 and 98? And boy, isn't that interesting, because it's really a whole lot easier when the numbers all match when you're trying to add than when the numbers are different. Agreed? It is. So let me add that little bit of structure that I mentioned before so that we can make sense of what's happening. We're just going to call this S. S for sum, but S. And that means that this second line is also S. So the reality is when I add these together, I have double the amount that I started with, right? Because I've added it to itself. And you know from your algebra that we could write that as 2S, just to remind ourselves that it's double. Do you have to write it that way? No, but you could write the word double next to it if that helps you too. You've doubled it. But in doubling it, man, you've made it a whole lot easier. How many 101s are there? There's 100 of them, right? There's 100 of these because it went from 1 to 100 to start with. That's 100 numbers. Okay, so I need to add 101 together 100 times. There's got to be an easier way to do that than just adding and adding and adding, and it's known as what? Multiplication. Yes, ma'am, it is, all of you. So what do we have? Well, what we really have is we have 100 times 101. So what is 100 times 101? Grab a calculator, multiply it out. You should be able to multiply it out as is, but you might want the calculator in a minute. What do you get when you multiply this? Okay, we get the 101, and then you get 2 more zeros at the end, like that, right? Because you multiply by 100. So you've got 10,100. But that's all well and good, but that's twice as much as I should have to the answer to the question, right? So if that's twice as much as I have, if that's twice the answer that I'm supposed to be getting, what is the answer I'm supposed to be getting?
5,000.
Yeah, 5,000 and then 50. 10,000 is 5,000, and then the 100 at the end is 50. And what we really did mathematically is we divided by 2, right? Because it was twice as big as it should have been. Now here's the cool thing. This process, he did it for the numbers from 1 to 100. But do you really think the numbers have to be 1 to 100? Nope. You could start at any number and you could end at any number, and this process will still work, and I'll show you an example next time. Not only that, but in your homework, what you're also going to find is it doesn't even have to be all of the numbers. Like this one was 1, 2, 3, 4. It was every single number. But there's also a way to make it a little bit more complicated and say, what if it's every other number? Or what if it's every 7th number? 7 would be terrible. I don't want to do that to you. 5th number, how's that? What if it's every 5th number? Is there a way to sort of generalize what's happening so that I could do this for something else that's a little bit less straightforward? And the answer, of course, is yes, but the process is almost the same. So that's where we're going to pick up next time. We're going to pick up on a similar example to this one, and we're going to change the numbers that are being used.